Hey all you cool cats and kittens, welcome to our Design Day presentation. We're Team Connect and Conquer, sponsored by Rincon Research Corporation and mentored by Dr. Greg Ogden. Our project is to perform object detection using Wi-Fi. Here's our agenda for today, and we're going to jump right in with our introduction. My name is Allie Gilbreth, and I'm a computer engineering major and the team lead for our project. The Tiger King character that best represents me is Eric Cowie, the head zookeeper.
My name is JJ Godasabi, and I'm a mechanical engineering major. The Tiger King character that best represents me is John Ranke.
My name's Rod Saeed, and I'm majoring in industrial engineering. If I was a Tiger King character, I would be the Walmart manager running Joe's presidential campaign.
My name is Ian Cinco, and I'm majoring in electrical engineering. My Tiger King character is Carol Baskin, and I did not kill my husband.
My name is Ariel Villasenor, and I'm majoring in computer engineering, and I'm Carol Baskin's dead husband.
So we're just going to start this off with a brief description of the problem. Rincon Research wanted to develop a system that would prevent destruction caused by drones or UAVs flying around with the potential to cause billions of dollars in damages, which can be prevented by security measures like proper detection. So our team was tasked in creating a prototype that can detect motion, such as a person walking, using the properties of Wi-Fi.
Moving on to our objectives, we were tasked by our sponsor with researching the capability and feasibility of developing a device with the capacity of detecting movement utilizing existing Wi-Fi infrastructure. Currently, there is not any commercially available system with the capability of this prototype. Other methods of object detection often use costly infrastructure to send and receive signals that would detect an object. But the opportunity with using Wi-Fi is that it is already prevalent in many locations. This would allow our prototype to theoretically connect to any network and map and detect surroundings.
As for our approach to the problem, we are primarily concerned on capturing channel state information, which contains details about how the Wi-Fi wave propagates through the area, and this shows how obstacles along the way might have moved over time. This comes as a complex value and can be deciphered from the incoming packets using our Wi-Fi card.
Having a background in malware detection, I proposed the idea of using a traditional sliding window algorithm. The sliding window algorithm has been used in object detection for images, so applying it to object detection using Wi-Fi seemed natural. We had considered machine learning, but with time constraints, the level of difficulty for us to properly learn machine learning, and the processing power required, we decided to move forward with a traditional algorithm.
To jump into our system requirements, a detailed list of our system requirements are included in the report, but I'll go over a few of the more essential requirements. Our requirements can be broken up into four main categories: performance, software, software design, and hardware. For performance, we have a requirement of automatically detecting movement within 10 minutes with an accuracy of greater than 75%. For our hardware requirements, we're aimed at portability and accessibility of the device.
Now on to our system endpoint design. Here you can see a diagram showing the three major components to our project: hardware, data algorithms, and the graphical user interface, or GUI. The hardware, or our system, will be running these algorithms and present it in a simple to understand GUI. On the next slide, we have the GUI, where changes in colors indicate a change in activity, which is the spectrogram.
For our hardware, beyond just capability, we consider portability as our major focus. We first considered the Wi-Fi card and a computer system that could both be capable of receiving and analyzing CSI data. There are only two Wi-Fi cards available with the capability currently: Intel Wi-Fi card and a Qualcomm Atheros Wi-Fi card. Secondly, we considered the computer that we would use to analyze the incoming data that could also serve our portability requirements as well as our budget. The Intel NUC was selected for both meeting the requirements and the compatibility of the Intel Wi-Fi card previously discussed. Next, we needed to find the correct antenna setup for the most accurate data collection. We decided to go with two directional antenna and one omnidirectional antenna. The three antennas are used in combination for an accurate picture of any movement in the environment. With these three major components selected, the corresponding peripheral hardware and components were chosen based on compatibility of the system and requirements for the device, such as a touchscreen, power bank, and a 3D printed chassis to hold it all.
We also needed to consider what software to install and create as well. The Linux 802.11 and Channel State Information Collection Tool, Jupyter Notebook, Octave, and Python were considered and then installed on our Intel NUC mini PC running Linux Ubuntu 12.04. Using the collection tool in Octave, we would be able to collect and convert the CSI from a binary file to a comprehensive CSV file. From there, we could utilize Python for our sliding window algorithm to run on the CSI data.
Moving on to our requirement verification, we used a test plan in order to measure accuracy and the time to detect. Originally, we were planning on using an empty space designed for these types of tests, but unfortunately, because of the pandemic, we instead had to create an isolated environment in our homes. To perform both the accuracy and time to detect tests, we would repeat 3 different actions 20 times. We would take these different actions as inputs to our sliding window algorithm and find our accuracy and detection time from its results.
We're going to do a demo on a running input file. So once we hit the begin detection button, you'll see the following output results. As you can see, a spectrogram is displayed as well as the time to detect, and it passed. We're going to hit view saved CSI, and we can also see that we're able to click and view some of our .dat files that we can collect.
For our cost requirement, we used a table in order to determine the average cost of the system. It turns out that the biggest cost was simply the NUC itself, and that each system would be well under the targeted cost of $1,000.
On to our results. Here are the results of our test used on a public data set. The data set contained CSV files with converted CSI for the listed motions as listed, just similar to our own. We ran our software in the files for each motion and achieved amazing results. As you can see, the algorithm's accuracy for all motions were well beyond our 75% accuracy requirement, leading to low false alarm rates as well. Our sliding window algorithm was able to detect the motion after, on average, 6 seconds, which is much less than the 10 minutes of our requirement.
Now we're going to close things off with some lessons learned. Overall, we overcame and learned from the problems we faced, which helped us not only finish our design, but grow as engineers. Even without face-to-face interaction due to the pandemic, we worked around software compatibility issues and debugged complex code. Throughout these challenges, we were able to work in a cross-functional team and expand our knowledge and experience on software design, Wi-Fi, and working in a team. Thank you to Rincon Research Corporation and Dr. Greg Ogden for their support throughout this project. Thank you for watching, and we hope you enjoyed this presentation as much as you liked Tiger King.